we solve one with a stub. Would that be all right?
Could you do an example of a shunt stub?
Mm-hmm. Yes. Okay. So example. Okay, matching with a stub. Okay, so consider the following. That's how also the final is going to be written. Somehow you can see how I write things. Consider the following transmission line configuration. Okay. And let me do this here. Okay, so you have one transmission line. In fact, a long transmission line. Let me see. I'm trying to think how I'm going to do that. Okay, it's one transmission line, but I'm going to split it in two parts just because it's going to be more convenient to talk about this. So there is another one and another one. Okay, and then, so it's the same line. And so these are connected. And this is A prime here, B, and B prime, C prime, D prime. And then at the end, we have a load. ZL. And we have Z naught here, Z naught there. What I would like you to do is to design it in such a way, and then you place like a shunt stub. Right? And let me put here ZS, even if we know that when it's shunt, it's better to work with admittances, but I will give it like this. And then say, fine, you know that the distance, this distance, this length rather, is D equals, say, what do you want to make that, like half a wavelength? And then you want to find D1, which is this, D2. Obviously, D1 and D2 are not independent. So if you find one, you know the other. And you want to find ZS. So practically what we want to find this, and this, when we know that ZL is equal, let me see, where, say where, ZL. Where Z naught is 50 ohms, ZL is say 100 minus J 50 ohms. Ah, uh, in fact, what I can do is instead of having that ZL, just as a variation, is to have a resistor. So here is what I will do. Have a resistor plus an inductor. And RL, say it's 100, and L is going to be 3 nanohenries. And so I erase that since I gave this. And the frequency F, which is the operating frequency, say it's 10 gigahertz. All right, so we're that. So find, we also have a source here. Okay, V naught, ZS. All right, so, and also the other thing that I'm giving you is that Z naught and, excuse me, V naught is 1 volt and Z naught is, ZS is also 50 ohms. ZS is 50 ohms. Okay, so now what I'm asking you to do, find D1, D2, and ZS so that you have maximum transfer, maximum power, transfer of power, transfer of power from the source to the load. Okay, so that is the problem. And so, as I always said, is that you will have, even if I give it to you, you will have to write it so you know exactly what I'm giving. You will have to write what is, as I will do here. I will write what is given. So as part of my solution, I will have to write what is given, other than making this figure, obviously, which I have, what is given. We know, first of all, that V naught is 1 volt. We know also that ZS is 50 ohms. We know that Z naught is 50 ohms. We know the total D, the whole from AA prime to DD prime, the whole distance, D is half a wavelength. We know that RL is ohms here, 100 ohms. I know that L, we know that L is 3 nanohenries. Okay, so this is everything we know.
I'm sorry. You said find ZS while ZS is given. Which ZS are we supposed to find?
Find, did I say, yeah, this one. I have the same. Thank you for changing. I need to use something else. I'll put Z not here. Okay, this one, the ZS, the stub, rather not the ZS of the source. So let me put this Z not, V not. Okay, so so let me erase then this one. Yeah, I was looking at the source when I wrote that. Okay, so that's good now. The only ZS we have is this. So I know, let me remove that then, so we don't get confused. All right. All right, so that's what we have. Okay, and then find D1, D2, and ZS. That's what we have to find here. Okay, and then what I said we have to do is to outline the solution. So we need to write an outline of the solution. And I will give points for writing this, as a matter of fact. Okay. When we write an outline, we always start from what we want to accomplish. And says here, the final thing we would like to accomplish here is to have maximum transfer of power from the source to the load. So let's focus on that. This is what they're asking us. Okay. So number one, to have maximum power transfer from load, from source to the load, we have to have the following things happening. A, what do I know from circuits? Under what conditions is maximum power transferred from a source to a load? Let me write it here. So here what we have is a source given to us, an internal impedance Z0, and then it's going to go to a line, but the line is going to present to this source an impedance. And this impedance that is going to be presented by the line is nothing else but the input impedance here. Do you agree with that?
Yes.
Okay. So practically this is going to be what the source is going to be, is going to see is this one. Okay, so that is the source. We are right at the end of the problem of what we need to achieve. To have maximum power from V naught to Z in, what do we need to satisfy? What condition we know from circuits that we need to satisfy? Is the go ahead.
Sorry.
Go ahead.
Assuming Z naught is strictly real, that means the input impedance at A prime has to be exactly the same as Z naught.
Exactly. So for maximum power transfer from circuit theory.
Can I ask a quick question to bounce off this?
Yes. Let me
So,
write this,
yes.
and then I will hear the question. Okay.
So what if Z naught in this case, like like not talking about characteristic impedance, but like the
Yeah,
in
the
this
internal.
circuit,
Yes.
if that was complex, and that would mean that the maximum power transfer would have to, that Z in would have at A prime would have to be the complex conjugate.
Yes.
But
Yes.
wouldn't that cause a reflection as well?
No, in fact, if you do the, well, a reflection to the source, you mean? Yeah,
Yes.
but if you do an analysis using Kirchhoff's laws, you will find out that the maximum real power is going to be satisfied if Z.
Oh, yes, that's true.
All
Okay.
right.
Yeah, I hadn't
Yes,
reconsidered that.
but the maximum Z in has, if that were say to be internal, let me write here internal. Let's assume that Z here is Z internal. All right, to the source. So that will have to be Z internal complex conjugate. And yes, it's true. And yes, it is true that there is going to be, obviously, you know, this is not an ideal, say, situation, because in an ideal case, the internal is going to be real, but under the given condition that Z internal is complex, that is the condition which is going to give you the maximum real transfer, power transfer.
Okay, that makes sense.
Yeah, and that is called the complex conjugate matching.
Mhm.
This is called
Thank you.
complex conjugate matching. Okay, so we need to make this happen. All right, what else is it that we need to make sure that we do to have maximum power transfer? After we do, let's call this equation 1, all right? After we make this apply, what else should we make sure we don't do? That we do not add any resistive elements between the source and the load. Why is that? Because if we add any resistive elements between the source and the load, then they are going to take part of the real power. Do you agree?
Yes.
Okay. So the second thing is do not add resistive elements. Okay, so now we put the two conditions for maximum power transfer. Okay, let's see. Now, if the condition is here, that the situation here is that I'm going from my load to ZS, I add ZS in shunt configuration, and then I'm moving by another length until I find this to be Z naught. So what I can do is to, instead of spending another additional length to find Z naught, I say, what if I make this one here to be Z naught? If I make this one to be Z naught, if I can do that, then any other, and then makes the reflection coefficient there 0, at any other point of the line, the input impedance is going to be Z naught. Is that true? Am I right when I make that statement? When we have a transmission line, say, let me write here. When you have a transmission line here like this, and has a characteristic impedance Z naught, is it not true that if I put Z naught here, at every point of the line, I'm going to see Z naught?
Yes.
Okay. So if I make this one the load of this line Z naught, and therefore the reflection coefficient here is going to be 0, right? So the reflection coefficient there is going to be 0. Then it's 0 everywhere else. So it's 0 here, it's 0 here, okay? So practically, since this is true, what now I have decided to do is to see whether I can specify D2 and ZS. So this is in fact nothing else. Let me write it here. This is my Z in at B prime, all right? So without normalize for a moment. So for now, I want to make that equal to Z naught. All right, I want to make that Z naught, and therefore to achieve this one, I will have to make this happen. See, so now as outline is to say that 2, I will need to make Z input at B prime to be equal to Z naught. That's another thing I have realized that I need to do. And if I do that, then see, so it goes, I'm going down from the end of the problem towards the beginning, all right? Because if I make this happen, then this happens here. This happens, all right? And then I have maximum transfer. So I have to make this equal 0. Excuse me, Z naught. So now I know that I have to make this one equal to Z naught. So at this point, what I will do is go on this section of the line and work on that one. So let me just take this point of the line. Okay, so I get copy. I'm still outlining my solution. So now I'm going to 3, put here, paste that. And what I want to do here is make this one, which is, this is B, make B prime, make B prime, Z input and B prime equal to Z naught. So now I have to go and try to do this on the Smith chart. So, so we'll work, that implies to do that, I will work with the Smith chart. Okay. 4, to work on the Smith chart, what do we need to do? We need to normalize all impedances. Okay? And we will start with ZL. But ZL, I don't know exactly ZL yet. To find ZL, I have to write it as J omega L. All right? So this is 100 plus J 2 pi F L. Now, let me calculate 2 pi F L. And that's going to be 2 pi, F is 10 to the 10, which is 10 times 10 to the 9, 10 gigahertz. And L is 3, 10 to minus 9 Henry. So that gives me this and that. And then I have 60 pi, all right, which is equivalent, let me see, 60. 60 times pi, 60 times pi equals 188 approximately. So 2 pi F L is approximately, it's 188 and a half, but just to make it less than a half, 188 ohms. Okay. So now I have ZL to be 100 plus J 188. So now I have to normalize it. ZL normalized is going to be 2 plus J, and I have to divide that by 50. Okay, 188 divided by 50. 3.76, 188 divided by 50. 3.76. All right, so I normalize that. And I don't have anything else to normalize because ZS, I don't know. I need to find it. Okay, so now, and I don't have to normalize a length yet. I need to find it. So now I have to go to the Smith chart. Do you have any questions so far? Now I can start with the solution, all right? So now I can start solving the problem. So far, I was just preparing it to solve it. So do you guys have any question before we start on the Smith chart? Okay, so let me go and find one. Find a Smith chart. And where do I have a Smith chart? There. Copy. That's not the one. Okay, I'll clean it for a second. Okay. Let me start with ZL. I need to find it first. So ZL is 2 here. 3.76, 3.76, 3.76 rather up here. It's here somewhere, 3.246876 is somewhere here. All right, so somewhere there. Okay, so this, let me go back here, go back here and here. So that is the load, and I will remove the other two. Okay, so now that we found it, I don't need those. So that is ZL. Here, ZL. All right. So now, let me, did I have that piece here? Yeah. So let me take this, copy down there, copy, put it down here so we have it nearby, paste. All right. And in fact, instead of this at the end, I have ZL now. Okay, so I have ZL. Okay, now I have to move. What that tells me is that as I move from the load towards the source, the generator, I will have to walk on this or to move along this line, which means that while I am on this line, and I'm going like this, I will have to move on the constant, on the constant VSWR circle, or the constant reflection coefficient circle, or the circle of the transmission line, as we call it. I have to move on the circle of the transmission line. But then when I arrive at CC prime, I will have to add something in parallel, which implies for me to do it easily, I will rather work with admittances. and not with impedances. So the one thing I'm going to do is to take this and change that into an admittance form. I don't have to do it. I will do it here just for convenience. So this one is going to be instead of, let me use a different color. I'll use this one. Instead of this, is going to be YL, normalized, and that's going to be YL. And instead of ZS there, I will put YS. Okay, YS, in fact, why do I need to do that red? Since I'm working on this with red. And then so here will be that. And instead of Z naught, obviously, I have Y naught. And everything is normalized with respect to Y naught. Okay, so I go from here there, just because it is in Shunt configuration, the stub. So how do I go from ZL to YL? First of all, I again have to write the transmission line circle, the circle of the transmission line, which is this one, and I will make it thick. And then, okay, so I will write it. No, did not take it. Okay. There. Okay. Extend it. Here. All right, more or less that one. I think maybe a little further out here. Okay, a little further out because it seems like the other side is, yeah. All right, so from here, which is the purple, I will have to draw the diameter that goes through that point. Here, that's YL. So let me put it here, YL here. Oh, I will do it like that. Okay. And after I found that, I don't need anymore this. So I found that here. All right. Now I did this. Now I need to move on this line. I need to start moving. Until I'm ready to add a stub, a load. But this load, which is an admittance, you remember what we said? It has to be reactive. We cannot add anything that has a resistive part in there. So YS has to be reactive only. All right, that is the reason. The reason is because we don't want to lose any power into resistors. And that's why we are going to have a YS, which in fact, when I said that here, that's what I meant. Let me add it in the outline. Here, you see that? What that means is that YS is reactive. Okay, so but how are we gonna do this? So the one important thing to keep in mind is the following. When I come, so I have the following things I'm trying to put into consideration. When I move on this line here like this, from the load, I'm moving from here, I'm moving this way. I will, when I start moving, I will come right before, like at CC prime, all right, before we add Z sub S or Y sub S. When I come here and I see an impedance or admittance, since I am in admittance form right now, but let's assume impedance here, all right? And that's gonna be the impedance at CC prime. So for this one here, it implies that when I look here, I will see an admittance at CC prime, since I am working with admittances. And since I'm on the Smith chart, it's gonna be normalized. So since Y sub S can only be reactive, number one, and since Z input, if you remember from before, since this one at BB prime has to be, remember what we said it has to be? Z naught. There, it has to be Z naught, which means that normalized Y in BB prime, it has to be 1. If that's the case, that also the admittance Y input at BB prime has to be 1. Okay? Which means in this circuit, if I look only at this part of the circuit, what I will find is the following. I can write it as, if this is B, B, C. I'm just trying to write this part of the circuit, B prime, C prime. Here we place YS, all right? And I will put it normalized since we are on the Smith chart. Here is the equivalent of Y or input CC prime, all right? What practically I see here. And here, my input is gonna be Y input BB prime from here. So that's how it looks. But in this small circuit, what we have from here is Y input at BB prime normalized is equal to YS plus Y input CC prime. All right? And YS is reactive. So if YS, the real part of YS is 0, that's what it means, reactive. So this is reactive. That means the real part is 0. Therefore, from here, it implies that the real part of Y input BB prime is going to be equal to the real part of Y input CC prime. Do you agree with that? Yes? No?
Yes.
Okay. So from there, since we want this to be 1, you see that here? We want this to be 1. So that is should be 1. So from here it tells us that we have to move on the Smith chart from here, obviously, along towards the generator, which is this direction. We have to move along that direction from where I am until I find the circle that corresponds to the resistive, the constant resistance circle that corresponds to 1. So I'm going, as you can see here, I'm traveling quite a bit because this circle that goes through 1, I'm going to write it for you, is, let me see, this is this one. That's the circle. And let me do it a little darker, a little thicker. That's the circle that has all of the normalized real part is 1. So I'm moving now along my circle. Okay, forgot this one. I'm moving until I find this red circle, which is here. So the point there, that point here, is my y is exactly this one. This one. All right? This one. The point that I found here, this is y input at CC prime. So this is y input. In fact, I don't need any more ZL if you like. I don't need that part. I can remove it back since I'm working with admittances. So this is y in and CC prime normalized. Okay, so that's so far so good. Now I wanna add something there as we saw from here, all right? So we are going to this one add a reactive part. So we are gonna keep the real part of y input CC prime. We're not gonna change it. We'll only change the reactive part. And we will have to find a reactive part that is gonna make the whole impedance, the whole admittance y in BB prime 1, which means we will have to find a reactive part, ys, that is gonna bring our point to the center of the Smith chart. So from here, I will move along this red line now, same, and I will move like this. But since I'm moving on the constant resistance circle, I don't really move. I don't move along the line. I just show that I'm changing the reactive part of my impedance, which means that while I'm going from y in CC prime to the center of the Smith chart, that point at the center of the Smith chart, this one here, is gonna be my y in at BB prime, which is normalized 1. So this is gonna be y in at BB prime. So practically, if I find the 2, and this is 1, all right? So I know the relationship between the two, And that tells me that ys is going to be y input bb prime minus y input cc prime. Here it tells me because in fact of this one, okay? Remember this. So I will find it. How much from here? In fact, I can read it immediately to tell you the truth because, well, or I can find it from here. How much is y input cc prime? This one, if I read it, is 1 plus j. And what is the j here? What I'm going to do, this one. And I'm going to do it like this and this. So if I move along the constant reactance circle, which is this one, then practically I find a reactance out there, which is here. And that, if I read it, is 0.2 here, 0.2. And then, where is 0.3? 0.2. I think that's 0.3, which I covered. Let me see. Yeah, 0.3. And then, so practically, I am somewhere here. Oh, it's somewhere here. That's kind of too thick, practically, to see it well. So I'm somewhere here. And it's 2.2, 2.2, 2.4, 6, 8, 2.9, say. So this one is going to be 2.9. So according to this formula there, which I'm going to take it and place it here, what do I conclude? I conclude from here that my ys normalized is equal, since I subtract from 1 y in cc prime, ys is minus j 2.9. So I found ys, okay? So let me see. What I need to do, one thing that I have not done yet, which I'm supposed to do, is to find D2. All right, so I need to find that because I have not calculated yet. How much is this? To find that, I need to go here and find, because that D2 is the distance I'm traveling to move from my YL DD prime to CC prime. So practically the distance I'm traveling between YL along this green circle with the arrows until I get to this point here. I need to find the distance. How do I find the distance? I'm connecting with green. Make it like this. I'm connecting this point here, the center of the chart, with the red point. And I find where I am on the yellow rim. The yellow rim means this one. And in fact, where I am there, it should be this is close to 0.47. Probably is close, this one. If I were to write it, it would be this one here. It will be 0.469 lambda. That's one. Then as I move along this green circle, along the arrows, I'm going through this point, which is 0.5 lambda, meaning that to go from there to 0.5 here, I made a a trip of about 17.031, which was, so this one here is 0.031 lambda. So 9 from 10, 1 and 6, no, exactly. So it's, yeah, I see 7, this is not 3. So let's try 9. So let's try to do it carefully. It's not 3. So it's 9, red. 9 from 1, from 0, 1 and 6, 7, 8, 0. That's what it is, lambda. That's that distance. And then from 0.5, which also turns into 0 again because it goes around and around forever, from there, and I write another line which connects the center of the chart with this one. All right, and I will make it a little thicker there. And then I will go here to see where I am. And that point is 0.2, say 1. 0.21. So I traveled by 0.081 plus another 0.2 I need to make it red. 0.21 lambda. So the total distance d2 is the sum of the two paths, 0.081 lambda plus 0.21 lambda. Okay, 0.21 lambda, which makes d2 to be 1, no, see, not that one, is 1, 1 and then 9, 2 lambda. And there, I shall 2. Okay, so that's d2. All right, so practically now I found everything that I needed. I needed to find d1, d2. I found d2, I need to remember it, how much it is, 0.291, 0.291, 0.291 lambda. I found that. How much was the total length? 0.5. So to find d1 is 0.5 lambda minus 0.291 lambda. All right, so I found d1. And how much is zs? It's asking for zs. And I have ys. All right, I found ys here to be minus j point or 2.9. Which means that zs will be 1 over ys and that is going to be 1 over minus j 2.9, which means zs is going to be j, and then since I'm 50 divided by 2.9, which means that zs will be j, and then 50 divided by 2.9, which makes it 17 point, say 3.2 ohms. So now I found everything. Okay, and I have it here, 17.2. So I go here, 17.2. Now, any questions before we go to power? Okay. What we're gonna do then, power. Since I was able to match the input at BB prime to 50 ohms. So practically everywhere on the line, which is from AA prime to BB prime, I have a perfect match, which means that whatever power goes from V naught into the line, it all goes eventually, it is absorbed by the resistor, the real power. So then all of the power that the real power that is going to go into the line is going to absorb by the resistor. So how are we going to find this power? How much it is, all right? So let's assume that I ask you to also find the power absorbed or delivered, absorbed, say by the resistor, by RL. Okay, how are we going to find this? What did we say we were going to make Z input of AA prime here? We said we were going to make it equal to Z naught. Is that not true? Yes? No?
Yes.
Okay. So if in this little circuit, how much is, let's try to take that little circuit and go down, copy. So we go here. So here, okay. So let's put a line here just to make sure. And remember, find real power delivered in two, rather, okay, paste. Okay, so we have this one here, and practically we have Z naught here. So from the source point of view, the source does not see RL. The source here sees Z naught. So the power, so the current here is going to be V naught divided by 2 Z naught. And the current, therefore, is going to be 1 divided by 100 amps, all right, which is going to be 10 to minus 2 amps. And the real power, P, is going to be VI, since they are not complex numbers, it's going to be 1 times 10 to minus 2, and that is watts. Why did I write it like this? All right, which is going to be 10 milliwatts. That's how much this source is going to give. And this 10 milliwatts is going to go all to R sub L. And that's a power that is going to be absorbed by our Bell.